Hi, I'm going to try this lesson to finish off the A-level work on amines. We've done most of it, but one of the aspects of A-level is synthesis. So they ask you questions about amines involved in a whole sequence of reactions. So sometimes you need to see where the reactions of alkenes fit amongst other ideas from other homologous series reactions that you've done. So this lesson is inherently going to be bitty and scrappy. I'm going to try and pull in ideas from a number of different things, past ideas. There will be future ideas that we'll discuss in future lessons, and of course the existing ideas last lesson that I did about excess haloalkanes reacting with amines and ammonia. So let's get started. If I try and get you to recap. If I try and get you to recap, do you remember when you had haloalkanes and you reacted haloalkanes with potassium cyanide? So, haloalkane reactions, nucleophilic substitution, the cyanide ion goes in, the X as a halogen gets kicked out, you get potassium halide formed as well. But the main thing I want to focus on is that we got a cyanide, or the modern name for cyanide, we got a nitrile. Now, that nitrile you can convert to an amine, hydrogen gas with nickel catalyst. Hydrogen gas, nickel catalyst converts that to our CH2 NH2. This primary amine is formed as a consequence of that, and the primary amine that you get is useful because that primary amine, we can react that with haloalkanes, maybe a different haloalkane, and turn it into a secondary, and then tertiary, and quaternary ammonium ion. So that we've done in the past. Now we're talking about amines. That's an amine, and now we've discussed how that would react with haloalkanes. The lone pair on the nitrogen would attack at the electron deficient carbon atom and go through that whole process that I described last lesson, about further reactions happening over and over and over again. That you're, provided you've got excess haloalkane, then you'll get the secondary will react further to give you the tertiary, and the tertiary will react further to give you the quaternary ammonium ions with the halide ions, obviously. And that's what we've done recently, that's what we've done last lesson, that's what we've done in previous lessons. Well, more than that, because these are nucleophiles, they will react with acyl chlorides or acid anhydrides Right, now, that is an electron deficient carbon center. that and that are both electron deficient carbon centers. So, nucleophile, the pair of electrons, the pair of electrons on the nitrogen, that pair of electrons can come along and make a bond with the carbon. Remember, the double bond in the carbonyl will open, they'll get an intermediate, and then that double bond will close, reform the carbonyl, kick out the chloride ion. Chloride ion gets kicked out, and you get an amide. Exactly the same reaction happens with acid anhydrides. Again, they would react to give an amide. These were reactions we did after carboxylic acids. We called the topic, we called it carboxylic acid derivatives, acyl chlorides and acid anhydrides. The acyl chlorides were great reactions, but they were too quick, they were dangerously quick, whereas acid anhydride reactions were much more manageable. So you may be asked to react an amine, you may be asked to react an amine with acid chlorides and acid anhydrides, and they would react to make amides. What else? Well, we've not mentioned anything about aromatics. So if we had an aromatic like nitrobenzene and we reacted it with hydrogen gas in the presence of nickel catalyst, you would get NH2, you get the phenylamine or aniline, and 2 lots of water. You don't have to use hydrogen gas and nickel catalyst. You can use tin and HCl. I've been through these kind of reactions in previous lessons. I've been through that reaction, and I've been through this reaction. And remember, I said I want you to learn that one of the very common reducing mixtures is tin and HCl, or zinc and HCl in different circumstances, because we have zinc in a school laboratory, we don't have tin as readily available in the school laboratory. So you might be asked to make an amine, and if it's aromatic, you'd make it this way. Having made it, then you might be asked to do various reactions of it in the course of synthesis. So in the course of reactions that require a whole scheme and multi-step reactions, these ideas may be mentioned. Now, I don't think I mentioned anything new in this video. I'm just trying to bring various things together. And you know what? I suppose as a teacher I'm wittering, I'm going on, and I'm rambling, which is fine. But where are you going to get all that knowledge from? Well, you're going to get it from each individual topic, understanding it, understand every topic, and then when you start doing synthesis questions, that's like questions that say, start with this starting molecule A and make a target molecule, say F. And you've got to go from A, convert A to B, B to C, C to D, D to E, and finally E to F. That whole scheme is going to have to come from your head using the knowledge from various different topics that we've taught you. So synthesis to me only really comes about successfully in a pupil's mind when the pupil understands every topic, every homologous series type reactions that we've done in the past, and can then use his or her intellect and intelligence to try and piece these jigsaw pieces together into one coherent synthesis scheme, where you can take a starting molecule and convert it to a finished final product molecule in the way that the question wants you to do. And it's only exam questions, practice at synthesis questions, that are going to get you that skill. I can witter for as long as you want here, but it's not going to help. You have to do it, and you have to do it using real questions. So good luck with that. That's the end, I think, of the amines topic.